All right, question 4 is the type of question we've seen many times before. We've got a chemical formula, we've got a proton NMR, carbon NMR, and IR spectrum. And our question is, what's the correct structure? So if you've done enough of these by now, you should know that a good first step is to always calculate degrees of unsaturation. And we get 5. Which again, hopefully we also know by now, is often a good sign that we've got an aromatic ring. Now, what do we see in the IR that's important? Well, primarily, I see this peak right here. What is a peak like that? Well, we can see down here, 1694. So that suggests it's a carbonyl. More specifically, it's most likely to be a ketone. Of the possible carbonyls we could have in this molecule, the ketone generally shows up at the lowest wave numbers. Now this one's even a little bit low for the ketone range, so that suggests to me that there's something next to the ketone which is giving it more single bond character and pushing it to lower wave numbers. So right now, just from the formula and the IR spectrum, I'm going to start with a structure like that. It gives us the aromatic ring and the ketone, which account for our 5 degrees of unsaturation. And by putting the ketone next to the aromatic ring, it also suggests to us that we have it conjugated with the aromatic ring. Now we've still got 3 more carbons and another oxygen to account for, so we're not yet done. But we've gotten off to a good start from the IR spectrum. Now we need to see, what does the proton NMR show us? And the answer is quite a bit. And the first thing that should jump out at us is something that's going to make us revise our opinion from our previous step. That's this peak at 10 ppm. Pretty much the only thing that shows up out here is an aldehyde. And so while initially we thought there might have been a ketone, we now know it has to be an aldehyde. Now I'm going to again put that aldehyde right on the aromatic ring, because at 1695 wave numbers, we know that that aldehyde has to have some sort of conjugation. Now, what else do I see? The next thing that gets my attention are these 2 doublets. Remember, anytime we have 2 doublets like this in the aromatic region, first of all, it confirms that we have an aromatic ring. Second thing is it tells us that we have this 1,4 or para type substitution. Now the question becomes, what else is coming off the aromatic ring? We know we have a total of 4 more carbons to place in this molecule. We also know that there has to be another oxygen. Additionally, we know that all 5 of these atoms, the oxygen as well as the 4 carbons, need to come off of this point in the aromatic ring. Because if we put them off of any other position in the aromatic ring, it's going to affect the substitution, or the splitting pattern in the proton NMR. Finally, we know it can't be an alcohol, or we would have seen an alcohol peak in the IR spectrum. But the other thing that jumps out to me are these 12 and 9 peaks. That means we're going to have a proton somewhere that is adjacent to multiple other carbons with hydrogens on them. In addition, we only have this one peak at 4 ppm for a carbon next to an oxygen. And the reason that that's important is what it means is we can't have something like this, CH2O, CH2, and so on. Because if we have something like that, that means we'd have 2 carbons next to the oxygen, and that means we would have 2 peaks in this 4 ppm range. So I'm going to start by putting the oxygen in here, and then just drawing a 4 carbon chain. And we'll see if that makes sense. So here we have a CH2 that's next to an oxygen. It would be a triplet because it's next to 2 hydrogens, so that works. Next we have a CH2 that's next to 2 different CH2s. So that would give us 2 plus 1 times 2 plus 1 for 9 total peaks. Here we have a CH2 that's next to a CH2 and next to a CH3, which would give us 12 peaks. And finally, this methyl group is next to 2, would give us a triplet. So this looks like it's a pretty good bet for our structure. We're just going to take one final step and look at our carbon NMR and confirm it. So just to redraw it, so we have our carbonyl here, we have our aromatic ring, and then each of these peaks corresponds very nicely to one of the carbons left in that alkyl chain.